Welcome, everyone. Welcome to this session of Geometry, Cosmology, Spirituality. It's been a while since I've done one of these. I think it was half a year. I think I did one at the last equinox. And now here I am again at this equinox because there's another significant cosmological alignment, both a solar eclipse and an equinox at the same time. Now, I'll describe what that entails in the images when I begin from now. Now, the drawing that we'll do after I've shown some slides is something called a Solomon's knot. It's a form that you find a lot in Greek mosaics, and it's come to have the association with Solomon. I'll talk about that a bit later. Now, the solar eclipse is due to happen in about, I think, about a quarter of an hour's time. Now, this is what's going on when you have a solar eclipse. You have Earth, let's say, on one side, the moon in the middle, and the sun on the right. So the sun is illuminating this side of the moon, and we obviously can't see that side of the moon. So it is essentially a new moon. But when there's a perfect alignment, as there's going to be very soon, or rather, yes, as it's going to be very soon, um, you have this eclipse through this particular straight line relationship. Now, a couple of weeks ago, we had a lunar eclipse, and the lunar eclipses always happen at the full moon. Solar eclipses always happen at the new moon. And this is the order in that case. So that's where you have Earth in the middle, and that obscures the light of the sun on the moon. So you have an eclipse moon. Now, this is all due to the fact that there is this thing known as the inclination of the moon. This is something I talk about in my book, The Cosmos in Stone, because this angle of the moon's inclination seems to be used in various Gothic cathedral designs, particularly, notably, the chapter house at York Minster, which is skewed by this angle of inclination of the moon. Now, this is it. We're looking at planet Earth, and there's the North and the South Pole, and the equator, and that 23.4 degree axial tilt. Now, this is why we have the solstices and the equinoxes. Now, that horizontal line, the ecliptic, that's the orbital plane of Earth around the Sun. Whereas, as you can see, the moon is on a slightly different orbital plane, which is inclined by just over 5 degrees. So it's only when the moon on its orbital plane passes across the ecliptic that you get these eclipses going on. Now, we can actually, what we're looking at here is essentially what's going on exactly because it's the equinox as well. So you need to imagine yourself in the position of the sun, illuminating planet Earth and the moon in front of you, and the moon is at the moment just passing in front. And you have obviously the equator as the part of Earth that's closest to the sun as well. So it is an equinoctial eclipse and new moon. Now, I mentioned that we're going to draw a Solomon's knot, and so I thought I'd take the opportunity of talking a bit more really about the tabernacle. I mean, I'll begin with the Temple of Solomon, and this is the one chapter heading in my book that rhymes, pi and 3 in the molten sea. The molten sea is a water container for priestly ablutions. Here it is here in the Temple of Solomon. So we've got the Temple of Solomon, the Holy of Holies, the holy place, the porch with the pillars, Yachin and Boaz, and then you have the molten sea here. Now, there's a particular description of the molten sea that has created a certain, I suppose, a certain amount of questions about the mathematical knowledge of the ancient Hebrews, because it appears to be suggesting in the description of the molten sea that the Hebrews thought that pi was equal to 3. Now, there's various things that have been said about it over the centuries, but what is generally assumed to be the case, I'll show you in a second when I show you an image of the circle, is that these two measurements are actually part of a relationship, well, I would say between pi and 3. So it's not that pi is looked upon as being equal to 3, but there is this significant relationship between pi and 3. Now, here is the quote from the first book of Kings. Then he made the sea of cast metal. It was round, 10 cubits from brim to brim and 5 cubits high, and a line of 30 cubits measured its circumference. So 10 by 30, 1 by 3. That's where this, I suppose, discussion comes from this particular quote. Now, various people have talked about this. John Michel talked about it in his books. This is how it would be suggested it needs to be looked at. So you'll see that the 10 cubit measurement with the red lines there, that is measured from the, I suppose, external part of the rim, whereas the internal part of the rim is what gets measured for the circumference. And so hence that is 30 cubits. Now, the reason why this arises is because of this relationship between pi and 3, which is essentially a relationship between 22 and 21. Now, if that sounds a bit odd, let me just describe that. I'll have to go right from the beginning and talk about just first of all pi. So you're probably aware pi is the measurement of the circumference of a circle in relation to the diameter, 1 to pi. Now, pi is what's known as an irrational. So it goes on to an indefinite amount of decimal places, as you can see here. I mean, it keeps on going on, it never ends. And these numbers never go into a repeating pattern of numbers. If they did, then it would be a rational number. So there's an approximation of pi that we know was used in the ancient world, 22 divided by 7, because as you can see with the first three numbers, the 3.14, it's very close to pure pi, but it then goes off in a different direction, and it actually creates one of these repeating decimals. So I'm highlighting it there in red. You can see it goes into this sequence of 6 repeating numbers, which you always get when you divide by 7. You get a combination of those 6 numbers. Now, what this means when we use rational approximations of these irrational measures that we get in geometric forms, it makes it, I suppose, more practical to use in the world of boundaries, let's say, because you can't have 3.14159265 bricks, whereas you can have 22 in relation to 7. So in this world of boundaries, using bounded numbers that perhaps approximate what could be just described as boundless numbers is a way of working. And so you have this interrelation between the boundless and the bounded, which is thought to be really what lies at the root of the Pythagorean philosophy, according to Philolaus, the Pythagorean. Now, this is what I was saying about this relationship of 22 to 21 being pi to 3, because if you do 21 divided by 7, you of course get 3. So 22 divided by 7 is that approximation of pi, 21 over 7 is 3. So the relationship of 22 to 21 is, in a sense, the relationship of pi to 3. Now, of course, having said that, that's if we're using this approximated version of pi. So 22 to 21 is the same as pi to 3 if we're using this type of pi. So in this sense, this difference between these numbers, so for instance, the distance of difference between these two red lines and the two green lines here is essentially a difference of 22 to 21. And so hence you have that pi and 3 relationship within this particular diagram of the molten sea. Now, this is, as you can see, it's page number 268 from my book. It is actually one of the chapters that's online, so you can access these chapters from my website, tonburygeometry.com. Now, there's a little footnote at the bottom there. I won't read it, but that is sort of the subject of that footnote is what I'm going to sort of move on to in relation to the way in which you get the same type of geometry as this in the Tabernacle. Now, the Tabernacle is the portable temple that preceded the Temple of Solomon, and its measurements were exactly half the measures of the Temple of Solomon. Now, the geometry of the Temple of Solomon and the Tabernacle, I would argue, comes from one of these forms here. This is a golden ratio pyramid triangle. It has a base of 2, and its two sloping sides are what would be called phi. That's the Greek letter phi, and then 1.618. That's the golden ratio. Phi is one of the names for the golden ratio. So you have 1.618 in the slanting edges and 2 as the baseline. Now, one of the things I show in my book is a particular diagram. This isn't in any book anyway. This is just something I discovered through my work in the design of Wales Cathedral, that you can produce a five-fold and tenfold geometric symmetry from one of these triangles. And of course, inevitably so because it's a golden ratio form. And the golden ratio within circular geometry brings forth 5- and 10-fold symmetry. So if we put in this circle here, which as you can see has the radius, which is the height of the pyramid triangle. And then if we go to the bottom of the pyramid triangle, to the midpoint of the baseline, we put another circle in which is smaller. Now, the relationship of difference between these two circles is 1 to 1.618 because this is the golden ratio. Now, as you can see, where the smaller circle cuts the larger circle, it gives 1/5 of the larger circle. And so you can put in a five-fold form, as I've done here. Now, with the smaller circle at the bottom, where it is cut by the larger circle, that gives 2/5 of that circle. So we can put in a smaller pentagram in there with 2 of the pentagram points, 2/5 of that smaller pentagram. Now, this is the geometry that I would say is used to produce the rectangle for the Temple of Solomon and the Tabernacle. Now, if we turn this pyramid triangle into a pyramid rhomb, like so, and as you can see, I've put in the larger circle from the bottom corner of the rhombus, and we have that circle in the middle. Now, this is where we produce this particular rectangle, which I believe is used for the temple and the tabernacle. Now, as you can see, the pentagram goes in, and if we then put in an upside down pentagram to go with that one, it produces a 10-pointed star, like so. And then the rectangle that you can derive from that, that very interestingly appears to be what's used for the ground plan of both the tabernacle and the Temple of Solomon. Obviously, like I say, at two different sizes. But there's very particular things about this rectangle which bring in some very interesting geometries. And that's really what I'm going to talk about just for the next while before we start drawing. The reason why I've taken such an interest in this and where I found this diagram is just through analysing the ground plan of Wales Cathedral. So as you can see, this point here, which is really the centre of the crossing, so the line going from the middle of this window to the middle of this window to here, the threshold of the Lady Chapel and the centre of the undercroft and the chapter house, which is above the undercroft. And then you can draw in this star in here, and the rectangle gives you very ideally the boundaries of the choir. Now, as you can see, there's this extra bit at the end, and that's the thing, that's the key to a lot of the geometries that are used, or the numbers that are used with this particular drawing. Now, first of all, just to get started, this dotted line here, this dotted line, if we were going to use this dotted line to find the measurement of this line here, so the short edge of the rectangle, what we'd need to do is to divide this distance by 2.618. Now, I'll describe 2.618 a little bit more in a second. Now, let's say, for instance, that we actually said that this dotted line was itself 2.618. Then if we divided it by 2.618, obviously we'd get 1. So we could then say that the edge here is 1. If this is 2.618, this is 1. Now, just to say what 2.618 is, it's actually phi squared, or golden ratio squared. 1.618 multiplied by 1.618 gives 2.618. This is one of those, I think, bits of mathematical magic that you get with the golden ratio. Now, through Fibonacci numbers, hopefully you're aware of them. If not, there's loads about them on the internet you can look up. But through Fibonacci numbers, you can get rational approximations of the golden ratio, but also of this number here, this 2.618 number. And the Fibonacci numbers I'm going to use are these ones down here I've put in, 55 and 21. They're not consecutive Fibonacci numbers. They have one number in between them, 34. So if you have these two numbers which have another number between them, that gives you approximations of 2.618. Now, what this gives you is 2.619. I won't say all of that number, but I've put that long number in so I can show you how this, again, this is a rational approximation of the golden ratio because it goes into one of these repeating decimals. So this is what I'm going to use as 2.618 when I'm calculating this diagram in a second. So the tabernacle. Now the tabernacle, the way in which it seems to use this geometry is like so. You have an enclosure around the tabernacle, which is 50 cubits by 100 cubits. And then if you put this rhombus diagram within the width of the tabernacle, that rectangle gives you where the tabernacle ground plan is. Now, here's a sort of an artist's image of the tabernacle. Here's the enclosure I'm talking about. It's 50 cubits by 100 cubits, and you have these wooden posts which are 5 cubits apart. And then you have the tabernacle ground plan here. Now, this is one of the versions of it where it's further back towards the back wall, but there are the ones you normally see are how I've got it here, where it's sort of 35 cubits forward from the back, or at least this midline is here. So the way we need to look at this is that we've got the larger rectangle, which is the enclosure, and the smaller rectangle, which is the ground plan of the building. So all of these other geometries are really just showing you how I produced this smaller rectangle here. So there are the measurements of the enclosure. And then with the tabernacle itself, as I said, it's half the size or half the measurements of the Temple of Solomon. The Temple of Solomon is 20 by 60 cubits. So the tabernacle is 10 by 30 cubits. Short edge of 10, long edge of 30. Now, another measurement that's very important here is the internal measurement of the tabernacle, which is 9 cubits. So externally it's 10, internally it's 9. Now, there are the posts that go in with 5 cubits between each one of them. And here is the dotted line. So this is the one that needs to be divided by 2.618, or what I'm going to do is the 2.619 number that I showed you. Now, because we have this measurement here, which is 50, half of that is obviously 25, and that's what this is. So I'm going to do 25 as the number which is divided by 2.619. So 25 divided by 2.619 gives this number here. Now, as you can see, it's another repeating decimal, but it's pretty close to the arithmetic mean between 10 and 9. So I suppose you could say that the measurements that we've got for this, which is from dividing this by 2.619, it's in between the external and the internal measure. Now, if we then use this measurement, so I've put the measurement down here, if we were to multiply 10 by 3, we'd obviously get 30. But this isn't 10, this is less than 10. So the very interesting thing that happens is if you multiply it by pi, by 22 over 7, then you get the 30. So there's this very interesting interaction between the golden ratio, or a rational form of the golden ratio, and a rational version of pi, which gives us, I suppose, the geometry of this particular form with its external measure of 10 and internal measure of 9. Now, the other thing about these two ratios, the 2.619 and the 22 over 7 measure, is that they actually have a very interesting relationship themselves. They have a very interesting rational relationship, very simple, and that is 5 to 6, as simple as that. So those two ratios relate to one another as 5 to 6. So if 55 over 21 is 5, then 22 over 7 is 6. Now, if you're wondering what on earth I'm talking about when I say that, I'll just describe it in more detail. If we take 55 over 21, we get this, 2.619. Now, if I divide that by 5, I get this number here, 0.523. And if I now multiply that 0.523 by 6, then I'll get the 22 over 7 number here, the pi. So this is how there's this relationship of 5 to 6 between them. Now, the other thing is that they both contain, well, one contains 21, the other contains 22. So we're back to this pi relationship of 22 to 21. Now, what I'm going to do is flip these two numbers around. So they're going to go to the other ratio, like so. So we now have 55 over 22, which is much simpler. It's just 5 over 2. And we have 21 over 7, which is much simpler. It's just 3. Now, in a certain sense, this is really the simplified version of what's actually going on with the tabernacle. It's just these very simple rectangles where you have a 50 by 100 cubit enclosure, and then you have a 10 by 30 cubic rectangle. So why have all of this other complicated geometry, giving all these funny numbers and bringing in the golden ratio and pi? Well, the reason for this seems to be to do with the rectangle itself. So the actual rectangle here that is 10 by 30. Now, let's see the 2.619 number up here. I'm just going to simplify that and turn it into 2.5. Now, if we have 25 divided by 2.5, we just get 10. So that gives us the 10 measure, very simply. And then if you look down, rather than beginning this one with 10 or with 9.5454, I'm going to begin it with 10. And then I can just say 10 and multiply it by 3, and that gives 30. So everything becomes very simple. So as I say, why use all of this other complicated geometry? Well, it seems to be to do with this rectangle itself, which isn't actually a 1 by 3 rectangle. Now here it is, you can see in the star, and here it is divided. Here's the 1, and then at the bottom you have the 1, 2, and the 3, but you have this extra bit added on, as you can see at the end. Now, because it's a piece of circular geometry, you'll never get a rational rectangle. It will always be an irrational rectangle. And so you end up with this extra little bit added on to the end. Now, what I'm going to do to that is change it very slightly, and so it also becomes rationalized. Now, what this essentially is 1/14th of a unit. Now, this is what then brings us into the realm of pi and 3, because this extra bit is essentially the arithmetic mean, the halfway point between pi and 3. So if you look over here, here is the 22 over 7 number. I'm actually going to double the 22 and the 7 to 44 over 14. Now below that, I'll put 3. And if I double the numbers that I was associating with 3, the 21 over 7, I'll double them. So it's 42 over 14. Whereas if we take this number of 3 units plus this extra little bit here, that is 43 over 14. So this seems to be why you have pi and the golden ratio all joining together to create this geometry of the tabernacle. Now, the thing about the tabernacle is, as I mentioned, it's half the dimensions of the Temple of Solomon. So if this is 20, then this would be 10, and then half of the length would be 30. So this would be the tabernacle. And it has the same measurements as the molten sea, 10 by 30. So the molten sea is showing this pi geometry in circular form, obviously, whereas the tabernacle is, I suppose, like an opened out version of those same measurements. Right, now I hope you managed to keep up with all those numbers. I always say I failed my maths GCSE when I did it when I was 16, and I scraped by on a retake. So I'm used to all these numbers because I talk about them all the time. But if you got a bit lost in them, I'm going to be putting this online, the recording, so you'll be able to have another look at them then. So to the drawing, let's look at this Solomon's knot. Now, it doesn't really have such a Jewish background, as it were. It's more what you find in Greek mosaics, but really through the Judeo-Christian tradition, where you've had this mixing of Greek culture with Jewish culture. That's seemingly how it's come to get its name. Now, in a certain sense, you could say that it does have a symbolic likeness to a form like the Star of David, in the way that there are these two forms that are sort of inverse in relation to each other, but interweaving. So you have this duality showing itself as one. So you have often a symbol of unity or eternity with a form like this. Now, I'm going to be teaching a course from the very end of October, where I'm going to be teaching people to draw the geometric patterns from Greek and Roman mosaics. So if you want to join that, if you like what we're about to do here, then feel free to join this course. You can get to it on my website. And as I say, from 31st of October to the 12th of December. So do join me for that, particularly if you enjoy the drawing that we're about to do. So let's get down to the drawing. I'll stop the share. And switch my camera on. Okay, I'll spotlight myself, everyone. Hello, everyone. I'm not in my usual place of drawing in Wales. I'm actually up in London, looking after my father, which is something I've done for about the past 2 years now, though my sister's with him at the moment. Right, let's get drawing. I shall put on the drawing camera. Now, this drawing I'm doing on a piece of A4. So A4 paper, and I'm having it in landscape. You can have it in portrait, to be honest, but the way I actually have it in landscape, because I'm going to start with a certain line, which is more suitable really to do if we have the paper in landscape orientation. Right, I'm going to draw a vertical line down the middle. If you want, you can sort of find um, the midpoint of the page, or roughly the midpoint. Um, I'm going to go just off the midpoint. I'm going to mark 6 inches from that edge there. That'll be slightly off center with that, but no big deal. Right, now comes the compasses measure. As ever, I work in inches. Now we want to set a radial measurement of 1¼ inches. Right, once you've got that 1¼ inches, go into the middle of the line, the middle of the vertical line as you have it. So it's a relatively small circle to begin with, but we're going to be expanding out from there and filling up the page like so. Right, keeping the same radius on the compasses, place the point of the compasses into the top of the circle, like so, and put in a semicircle. Now we're going to repeat that from the bottom of the circle as well. Right, so I'm going to get a bisector cross, one here and one here. So in a way that if you do geometry regularly, you'll no doubt find this to be a very familiar move, getting the bisector crosses in place. So getting that small cross there using those 2 points. And an equivalent one on the other side. All right, as we generally do when we put in the bisector crosses, we then put in the bisector line, which hopefully, if we're working accurately will go through the center of the circle. Now the next step is to use these 2 points that we've now established to do a couple more semicircles like the other ones, but obviously orientated differently, so that we get these 4 petals. Now I've just realized actually we might need to, well, this line, I need to extend my line just a little bit more in this direction. We're going to go just a little bit beyond the crosses. So you'll find out whether you've got the right amount of line here in a second with what we're going to do next. Because what I'm now going to do with the same radial measurement as we've been using up to now, I'm going to go to these 4 directions of, let's say, north, south, east, west, and mark further out on each line. So for instance, I'm going to do that. And then the equivalent thing from the other 4 directions. So that will mean that obviously now I'm going to go from there. Right, these 4 points that I've just produced. Now make sure that you use the mark you've just made, not one of the crosses. We're going to draw in a square, diagonal square relationship, and you should hopefully find that it just brushes over the tip, or the 4 tips of the petals. Right, the next thing I'm going to do, I mean, I'll show you, this is what we're working towards. I'm going to put, you might see a few highlighted points here. That's where I'm going to put certain dots now. I mean, to be honest, you can put them in any sort of direction coming out from here, but just because I'm keeping the ruler horizontal, I'm making them go out in this direction. So I'm going to go from the tip of that petal just out horizontally. I mean, it doesn't even matter if your ruler's a bit wonky like that, just as long as you're drawing from that tip of that petal. Now, you'll see what I'm going to do is 1.5 inches, and I'm going to mark off quarter inches. So there's going to be 1, 2, 3, 4, 5, 6 marks, which I'm going to make. Now you can line your ruler up with this point as well if you want, if you do want to sort of do it in alignment. So I'm going to go 1, 2, 3, 4, 5, 6. Now I don't know if you can see them, perhaps I'll make them a bit stronger. Now you should hopefully find that if you put the point of your compasses on the tip of that petal there, you should find that the measurement on your compasses is actually the same as, well, the fifth one, the fifth mark out of 6. And so using that, I'm going to actually draw in um, this one here, which obviously takes in one of those marks. And I'm going to do the equivalent thing from all 4 petal tips. Now I'm going to do equivalent semicircles again in all 4 quarters, which use these dots here as measurements. So I'm going to actually go to the larger measurement now, so that the 6th mark that I made, and I'll do that larger semicircle from all 4 positions. And I'm just going to keep going from there. So now I'm obviously going to go to smaller measure and just using those marks that I've made. And obviously I only needed to make them in 1/4 because then I can obviously just sort of refer the same um, radial measure to the other quarters. King Solomon is associated with various geometric forms, often associated with, I suppose you could say, a sort of magical symbolism. Um, uh, the Seal of Solomon, so called, is sometimes that's the name of a 6-pointed star, sometimes a 5-pointed star, and it's generally from a story known as the Testament of Solomon, which I think I've mentioned in previous talks, in which Solomon subdues demons with a star, geometric star on a ring that he's wearing, and he then gets the demons to build the temple. So it's a very interesting story, I suppose, about the idea of subduing the energies of the soul that can get caught up in, I suppose, a chaotic engagement with earthly things and putting them to work on something that is divinely inspired, something that is ordered and cosmic and beautiful. And so this Solomon's Knot is sort of like another one really from that set of forms that you get that um, are symbolic forms associated with wisdom and spiritual knowledge. And this is why Sir Gawain has a pentagram on his shield. It says it's the sign of Solomon. And this, I suppose you could say, is what he uses for his internal warfare, his shield with the pentagram to subdue demons. Because chivalry is very clearly an inner path, as well as having sort of expected outwards modes of conduct. It is as much of an internal path, and so the shield is for internal warfare. And perhaps if we did our internal warfare, we might not have so many external wars. Now, I don't know about you, there's a part of me that could just leave this as it is now. I like this as it is now, but this is just a step along the way. So yes, when the seal of Solomon is spoken of, it's a seal on a ring. That's why it's called a seal, because it's the ring on the seal, or the seal on a ring, sorry. Right, the next thing I'm going to do is well, you can see in this finished version here, there are these semicircles like so, and then we've got these lines joining up with the semicircles. So perhaps that gives you an idea of what with the next thing. I'm going to gradually work my way across, linking up equivalent semicircles like this. Now, I'm not going to do it too heavily because don't want to have lines that are too strong in the background because we're only going to be using some of these lines here. And so there'll be this sort of interweaving of lines as well. So perhaps you don't need to do them not too strong. So obviously you don't do the middle line here, you leave that blank. I'm only joining up um, the semicircles. Now, at this stage, you might want to put a piece of tracing paper over. I'm actually going to just go straight down onto here, but with quite a heavy and blunt pencil. This is a 3B pencil. And I'm going to also freehand it because the thing about these mosaics is that, mosaics by their very nature, they're quite organic. They don't have these smooth, perfect geometries to them. So I quite like the idea of doing it by hand. Obviously, I'm going to try and be accurate, but I'm not going to go out of my way to be really, really accurate. I'm going to have just like something that follows the lines that we have here. And as I say, I'm going to use a much stronger line. Now I'll draw in a particular order. I'm going to turn it like this to begin with. And I'm going to do all of these semicircles in this top part here. And I'm going to do this with um, all four of these areas. Now, obviously, you're welcome to use the compasses if you want, but yeah, I quite like the wonkiness of the hands drawn. Right, I'm going to continue from here, and it'd be best to watch at this point, or if you can't, then watch in the recording that I'll put on the YouTube channel, because this is how we need to get the weave. So see, the lines are going to come down here, and they're going to go over and then under, and over and under. So there's a particular order I'm going to do it. I mean, there's various different ways that we can do this, but the important thing is to, I suppose, stop at the correct line. So I'm going to slant it over slightly. Now I'm going to go from this outer semicircle here, and again, I'll just keep on doing it freehand. Now I'm going to go as far So I'll go as far as I'm going to go, and then I'll point out where I stopped. Right, so I've gone as far as, if you see this little semicircle here, where this end of the little semicircle, the line that would be coming out of that, that's as far as I've gone. And I'm going to do the same with uh, the other um, the other lines. Now you'll notice I didn't draw the most outer line, that square, that diagonal square we drew. I'm not putting in the lines of that square. They're the ones that don't go in. So be careful not to put that one in. Right, now having done this, I'm going to put in a few extra little lines here that take me up as far as the first line that I just drew. So just these little bits here that I'm putting in. And this is what we'll do on each occasion. We'll sort of put in those lines, those little bits like that. And so now you can see these lines are going under these ones here, which are going that way. Now, I suppose it's probably most straightforward if I just turn the paper around and then do the same thing, well, the equivalent thing from a similar sort of perspective. So again, I stop this line. If I follow that little semicircle around, that's where it stops. And having done these lines, I'll then put these little ones in again, these little bits. One, two, three, four, five, six. And then I'll turn around another 90 degrees and start again. And before you know it, it's done. Okay, everyone, I'm not going to color it. I'm going to describe the shading that I've done and obviously use whichever colors you feel drawn towards. I mean, they're often quite ochre colors that are used in the mosaics. I mean, if you look up Solomon's Knot, you'll see loads of examples in mosaics. The coloring that's often done in these Solomon knots, as you can see, let's look at each form. There's a dark area in the middle and a dark area on the outside. And then going from the inner to the outer, you have these three different shades. So I've left that one just plain white and then shaded this one a bit and then shaded that one a bit more until I ended up in the very dark shade again. And I did the equivalent thing with this one as well. But do feel free to use some color. I've just done, the pencil shading, just because it really shows the tones in a very effective way. So, like I said, if you enjoyed drawing that, and if you want to draw some more mosaics, then do join me on this course. As I say, details on my website. Right, I'll just say a final goodbye. If anyone is around Wells next weekend, there's going to be an event. It's also happened last year on the Michaelmas weekend. Rupert Sheldrake, the scientist, he owns a bit of land just outside Wells, and he sponsors a patronal evensong at the Church of St Michael and All Angels in Dinder, which is just by the land that he owns. Now, anyone can go. He pays for a reception after the evensong, and he'll also be, if the weather's good, leading a walk up to this sort of hill, this wooded hill that is called St Michael's Wood, which is his piece of land. So for a bit of a wander up there. It's in the Dragon Legend area of Wells, and it looks over Glastonbury Tor as well as down on the Worms Tor, where the local dragon legend is. So if you're around Wells and you want to go to that, it's in a village called Dinder, and 3 o'clock, I think that's when we'll go for a walk. If the weather's not good, I might give a talk. I don't know, we'll just sort of see. So I hope you've enjoyed this session, and hopefully I'll see you again at some point soon. I hope you have a good week. And here we are in this very ideal alignment between Sun, Moon, Earth, and the equatorial plane of Earth. Right, have a good evening or a good day, depending on where you're coming in from. And I'll see you again sometime soon, hopefully.
Thank you very much, Tom.
Okay, thanks for coming, everyone.
Tom, bless you thousandfold.
Thanks, Tom.